Bismillahirrahmanirrahim. In this lecture, we are going to study synchronous motor operation, its torque speed characteristics, and effect of load change on the synchronous motor. First of all, synchronous motor torque speed characteristic curve. Synchronous motors supply power to load that are basically constant speed devices. There are some applications in which we just need the constant speed regardless of the load and regardless of the torque, like conveyor belts or lifts, where load may be different but we need the constant speed. In these applications, synchronous motor is used because synchronous motor have constant speed. Why? Because there is one stator magnetic field synchronous speed and rotor is locked. Rotor magnetic field is locked with the stator magnetic field and rotor is moving with the constant speed as the stator magnetic field rotates. So change of load will not affect the rotor speed, and rotor will continue to move its synchronous speed. That's why synchronous motors are the constant speed devices. So the resulting torque speed characteristic curve is shown in figure, in which figure you can see that one is torque induced and here is the speed, and if this is torque induced and rotor is moving with synchronous speed, which is n synchronous. As the torque is increasing, speed will not affect. So torque is not affecting the speed will remain constant. If this is the rated torque, then this will be the pull out torque, the maximum torque that a motor can bear, which is the pull out torque. Um, if we increase further load than this pull out torque, then motor will lose synchronization and some jerking motor will start jerking. So motor will move with the constant speed. Torque is increasing, it will not affect the speed, and motor continue to move with the synchronous speed. And the speed regulation, as speed is not changing, the speed regulation of synchronous motor is 0%. The steady state speed of the motor is constant from no load all the way up to the maximum torque that the motor can supply, called the pull out torque. So the speed regulation of this is 0%. Further, we already know that the torque induced is equal to K into B or B net sine delta, and in electrical terms torque induced is equal to 3V phase EA sine delta over omega m xs. This formula we already derived in the previous chapter for the synchronous generator, so same hold for the synchronous motor. So the maximum or pull out torque occurs when delta is equal to 90 degree. When this delta will become 90 degree and sine of delta will become 1, then the maximum torque or pull out torque will occur. However, the pull out torque typically 3 times the full load torque of the machine. When the torque on the shaft of a synchronous motor exceeds the pull out torque, the rotor can no longer remain locked to the stator and rotor start to slip behind them and whole motor vibrates severely and start jerking, and this process is known as slipping poles. The loss of synchronization after the pull out torque is exceeded is known as slipping poles. And the maximum pull-out torque can be given as if sine delta is equal to 1, then torque induced in magnetic quantities is K B or B net, and in electrical quantities it will become 3 V phase EA over omega m xs. So this is the maximum pull-out torque. So from this equation you can see that torque induced depends upon EA. So EA we know depends upon field current. So if we increase the field current, we can increase the maximum pull-out torque, which is T maximum. We can increase the value of the maximum pull-out torque by increasing the field current. However, in books state that these equations indicates that larger the field current, the greater the maximum torque of the motor. There is therefore a stability advantage in operating the motor with a larger field current. So if we operate motor with the larger field current, then motor can bear maximum load and can induce the maximum torque. So the next heading is effect of load change on a synchronous motor. Till now we study the effect of load change on the speed. We see that when we increase the loads, the speed will remain constant and the torque induced will increase. So now we also see that which parameters of the synchronous motor will change when load increases. If a load is attached to the shaft of a synchronous motor, the motor will develop enough torque to keep the motor and its load turning at a synchronous speed. So motor will run at the same speed, synchronous speed. So what happens when the load is changed on a synchronous motor? So when the load on the synchronous motor is changed, on the motor is increased, the rotor will initially slow down a little. As it does, the torque angle delta becomes larger and the induced torque increases. As torque induced is equal to K into BR B net sine of delta. When this delta will increase, the whole term will increase and torque induced will increase. When torque induced will increase, the increase in induced torque eventually speeds the rotor back up and the rotor again turns at synchronous speed but with a larger torque angle delta. Now torque angle is increased but motor is moving with the synchronous speed, but anyhow its torque angle now increased. So when this figure shows the motor phasor diagram before the load are increased. In normal case, at no load, when motor is running, its phasor diagram is this. At no load, normally synchronous motor are running with leading current. This is V phase. This is EA. And this is J of XS IA. This phasor diagram we already drive in the previous lecture. The angle between V phase and EA is the delta. This is the phasor diagram at no load. So when load on the motor increases, then what happens? When load on the motor increases, the internal generated voltage EA, which is this one EA, as we know, EA is equal to K of phi of omega, and this phi depends upon field current and this is the rotor speed. As when load increase, speed will not change. We already studied that speed will remain constant because of the stator magnetic field moving with the constant speed and rotor is locked with the stator magnetic field, so this speed will remain constant. And if is the external parameter and no one change the if externally, so if will remain constant. So at the end phi and omega will remain constant, so ea will remain constant. So when the load on the motor increase, ea will remain constant. So the thing change as the load increases is the delta, which is this angle between V phase and EA. So as the load increases, EA swings down in the manner shown in figure. But we already studied that the magnitude of EA will remain constant. So this magnitude will remain constant. So then this will be EA1 and this will be delta. And when load increase, the value of IA also increases. So as EA swings down further and further, the quantity J of X as IA has to increase to reach from the tip of EA to V phase. So when when load further increase, EA will move like that, and then IA will increase like that. So as a resultant, current angle also changing with V phase, and therefore the armature current IA also increases. Notice that the power factor angle theta, which is in between V phase and IA, if this is theta and this is theta 1, is decreasing, and when motor is running with some load, so it's so it is becoming less and less leading and more lagging. So notice that the power factor angle theta changed to becoming less and less leading and then more and more lagging. So this is the nature of the synchronous motor. When the load on the synchronous motor increases, for example, if load increases to this one, this is J of X as IA, number 4, EA 4. So then IA will become here, and now IA is lagging. So when load on the synchronous motor increases, so its current becoming less and less leading and more lagging. So that's how these parameters change when we increase the load. Number one is the delta. The delta will increase. When delta will increase, EA will swing down and the nature of IA will change. At no load, IA is leading, but at the maximum load, at higher load, IA will become less leading and then become lagging. So now example 6.1. A 208 volt 45 kVA 0.8 power factor leading delta connected 60 Hz synchronous machine has a synchronous reactance of 2.5 ohm and a negligible armature resistance. Its friction and windage losses are 1.5 kilowatt and core losses are 1 kilowatt. Initially, the shaft is supplying 15 horsepower load, and the motor power factor is 0.8 leading. Number 1. Sketch the phasor diagram of this motor and find the values of IA, IL and EA. This is the part A. Initially the motor output power is 15 horsepower. This is output P out. Initially the motor output power is 15 horsepower. This corresponds to an output of P out is equal to 15 into 11.19 in terms of kilowatt, and P in will be P out plus P friction and windage plus P core plus P electric or copper losses. Adding these, P in will become 13.69 kilowatt. P in is equal to under root 3 V terminal IL cos of theta. So from here IL is equal to P in divided by under root 3 V terminal cos of theta, and IL is equal to 47.5 ampere. As the motor is delta connected, so therefore IA will become 47.5 divided by under root 3, it will become 27.4 leading. And EA, as we know, EA formula is V phase minus J of excess IA minus RA IA. When here RA is 0, so this term will be neglected. So remaining by putting values and solving them, EA will become 255 angle minus 12.4 degree. So the phasor diagram looks like this, same as we drive before, and its values are these one. Now part B. Part B states that assume that the shaft load is now increased to 30 horsepower, that P out is now increases to 30 horsepower. Sketch the behavior of the phasor diagram in response to this change. As we already know, when the load is increased, then delta will increase, and this current will become less leading. As shown, the phasor diagram looks like this, but the magnitude of EA will remain constant. Its angle will change. It looks like this. As the power on the shaft is increased to 30 horsepower, the shaft slows momentarily and the internal generated voltage EA swings out to a larger angle delta while maintaining a constant magnitude. The resulting phasor diagram is shown in figure. Now part C. In part C, find IA, IL and EA after the load change. And what is the new motor power factor. As we know that the power factor will also change when the load increases. So now again P in will become P out plus P friction and windage plus P core plus P copper loss. Solving this, P in will become 24.88 kilowatt, and in order to calculate, as we know, P can be given as here like this: 3 V phase EA sin delta over XS, and from here delta will be equal to sine of inverse XSP over 3 V phase EA. Putting all values and solving this, delta will become 23 degree and EA is 355 angle minus 23 degree. So this is wrong again here, that this is not 355, it is 255 angle minus 23 degrees, because magnitude will remain constant, just this value will change. So from here IA V phase minus EA over J of XS, from this formula V phase minus J of XS IA. So by solving this, IA will become 41.2 angle 15 degree. Now you can see the magnitude of the current will increase as load increases, but its power factor decreases. This is the delta connected, so line current will be under root 3 IA, which is 71.4 ampere, and the final power factor cos of minus 15 degree will be 0.966 leading. So this is the example 6.1. Now that's end from this lecture.